The last speaker before the break. The last speaker before the break is Indranath Sengupta, and he's from IIT Gandhinagar. And his topic is some results on numerical semigroup rings. Please.
Martin, I think there is a question to Professor Herzog. If you see the chat box, maybe.
Yes, but it was not really complete. Now it is complete. Okay. I think maybe we can answer this question after your talk.
Okay, fine. Okay, so I'm clearly audible, right?
Yes.
Okay. So thank you so much, Martin, for this introduction, and thank you very much to the committee for inviting me, especially to Apurva. I mean, arranging this in such a short time is something extraordinary, I must say that. Okay, so this is the topic, and you have already heard a talk from Professor Herzog, who is a known expert on this in this area. So really speaking, probably you would find it a repetition, but just some new thoughts which has occurred in recent years. I would like to share that with you, but I will start with these three articles by Professor Patil, and which is kind of my entry point to this area of numerical semigroups and numerical semigroup rings. And I joined IISc Bangalore in 1994, and when he kindly agreed to be my PhD supervisor, and I worked with him. And these are the three sources which kind of gave me the necessary background. So these are the, and you will see that I will talk about some results. Of course, it's impossible to say everything he has done. There are lots of things, lots of results he has proved. Just, I'll be a little choosy, and I will just also say that some new thoughts, as I've already mentioned. Okay, so this is some basics of numerical semigroups. You have already heard from Professor Herzog. He has already mentioned that. So interestingly, I'm just sticking to the, mostly I'm sticking to the notations that Patil used in his papers. So this n is the set of natural numbers together with 0. And we are using this gamma for the numerical semigroup, which is an additive submonoid of n, such that it is finitely complemented. You know, this is the definition of a numerical semigroup. And you can, in fact, prove these with not much difficulty, that actually you can prove that every numerical semigroup has a unique minimal generating set. And then the GCD of these elements is 1, as you have already heard in Professor Herzog's talk. And every non-trivial submonoid of n is isomorphic to a unique numerical semigroup. So these are, in fact, very nice kind of results. And once you know the definition, they follow with a little bit of effort. And now comes this definition of the conductor and the Frobenius number. So the GCD1 condition automatically makes it finitely complemented, etc. And therefore, you will see that there will be a stage from that onwards, everything will be inside the semigroup gamma, and that stage, that number is what we call the conductor, usually denoted by C. And the previous one, which is obviously not there in gamma, that is called the Frobenius. And this is, of course, still a very hard thing that like people make various efforts to give bounds, to give calculations for Frobenius. There are also the computer scientists interested in this problem and things like that. Okay. Now, and also what Professor Herzog mentioned is that the result by Kuhns on the connecting the Gorenstein monomial curves with the symmetric numerical semigroup. There, of course, the conductor ideal, these things play a very important role when you are showing that the value semigroup is actually symmetric. Okay. And now again, as I have said, I am using Professor Patil's notations. So this was the notation that he used in his paper, that this is delta. So gamma, remember, gamma is the numerical semigroup, and gamma plus is the set without 0. And then look at those alpha non-negative integers, such that when you add every element of gamma dash gamma plus to this, then it lands inside gamma. Okay, so this set is this set delta, and then you remove the elements of, oops, I'm sorry, this I meant gamma. Okay, so you remove the elements of gamma. Obviously, if you just take these elements of gamma, they would obviously belong to, when you add them with the elements of gamma plus, they would belong to gamma. So if you just throw away the elements of gamma, okay, then what you get is this set is what is called the Pseudorubinius. In fact, in the previous talk, it was denoted by PF of S. So this is our Pseudorubinius. Now this set also happens to be very, very interesting, especially from the standpoint that I'm going to talk about, or what Professor Patil has done. And a few more notations. And then if I assume that this is a generating set with GCD1, okay, and if you, in fact, it's better to take them to be minimal and things like that to avoid redundancy. And then the smallest non-zero element, you call that the multiplicity of the numerical semigroup. And then, well, here I am just saying the Aperi set with respect to the multiplicity, but it is not necessary. You can in fact define the Aperi set with respect to any non-zero element of the numerical semigroup. That goes perfectly all right. But let us do it only for n for the time being, because that serves the purpose. And later on, I will make a comment. Okay, so this is how we denote this set by the s suffix n. Remember, m is the smallest element. So here we are taking that to be m0, the smallest element in the generating set. Okay, and then this is the definition, which is set of all those elements such that, oops, sorry, I mean the set of all those gamma, such that x minus gamma is not in M. So there's a typo. Okay, and this is precisely the set of M0 non-negative integers, or rather M non-negative integers, giving for each I between 0 to M minus 1, the smallest integer in gamma congruent to I modulo M. I mean, there is some, I think I better correct it immediately. Because I have already M, and this is also M. Okay, yeah. Now comes this very important theorem from this paper of which was published in 1990. I showed you those three in the list. First is thesis, and then a couple of papers. So where they described this set explicitly for an almost arithmetic sequence. You have already heard what an almost arithmetic sequence is. That means this is a string of, this is of E integers such that all but one form an arithmetic progression. And interesting enough, actually, this is very sorry, I'm not able to recall the exact year, but this calculation of Aperi set, understanding the Aperi set actually holds the key to various results. It's a very important thing to understand a numerical semigroup. Well, there are various approaches. Well, I would not say various. There are definitely some other approaches, and one is by the continued fractions by Alphonsine. I will add the exact details later on before I share the slides. So the point is that there are some ways to understand. Okay, I mean, it's mostly a Diophantine problem. You can understand that you are trying to find out the smallest ones congruent to I modulo M, and there are ways to try that. And once you know the Aperi set, you know a lot of things. In fact, I will be telling you what all they did in this paper and in the subsequent papers. You can understand that it's mostly coming from the Aperi set. Okay. Okay. So now let me quickly tell you what all were actually proved. I mean, at least some of the results, as I've already said, that assuming that K is a field of characteristic 0, let O be a curve in the affine E space over K with the relation ideal P. Given E, are there upper bounds on the minimal number of generators of the derivation module over K and the minimal number of generators of the relation ideal P? As I have said, I am using exactly Patil's notation. So this is how they have written in the paper. I am sticking to that. So now this is, and also this is the comment they have made, that they observed a striking similarity in several cases between the behaviors of mu of dark A O and mu of P. And indeed, so it still actually is very, very interesting. You will see from another perspective also. So here, these are the immediate observations that when your E is 1, remember E is the embedding dimension, because if we assume that there are exactly E integers, if we assume that there are exactly E integers, they minimally generated the numerical semigroup, etc. So this E is what is called the embedding dimension, and M or M0 is the multiplicity. Okay. Now, if the embedding dimension is 1, then it is, of course, you can immediately see that what would be your mu P and mu of dark O. Now, the interesting thing starts when you have E equal to 2, then you can again prove that mu P is 1, but mu of dark O is at most 2. Okay. And in fact, it is Kunz and Walby followed by explicit demonstration of these derivations in Patil Singh's paper of 1990. And then comes the E equal to 3 case. Again, the question is, what can you say about mu P and mu dark A? Oh, remember, we still do not have any assumption on these integers M0 to ME minus 1. Still, they are arbitrary. The moment you assume certain things like almost arithmetic, etc., you start getting more definite results. But in general, up to E equal to 3. Now, this is a very interesting result by Moe in 1979, where he actually demonstrated, he gave a family of space curves, which is for which mu P is unbounded, but that is not a monomial curve. Okay, so that does not have a monomial parameterization. So, or rather, that is not given by a numerical semigroup, right? Okay, so therefore, in this case, mu P is unbounded, but not the monomial situation. But in general, the question is what we have asked here, for that, this answer is actually, well, it is not true that you always have a bound. You can create families for which it is unbounded. And then this is a result in that paper. They showed that for the same family, the mu of dark AO is also unbounded. Okay, so this is the story up to equal to 3, and for E greater than or equal to 4 also, seen things don't get any better. In fact, you do create a lot of families for which mu P is unbounded and mu dark AO is unbounded, etc. Okay. Okay, so now comes more definite cases, that what I have said just now, that if you have a situation, if you assume that the integers, they are spatial in the sense they are almost arithmetic sequence, what does it mean? That means at most one is is not behaving well, but the rest of them, E minus one of them, they are forming an arithmetic progression. Then this is the result that they have proved, that E being the embedding dimension. So for a given E, this mu dark O and mu P, they are bounded above by this beautiful polynomial functions of E. Okay, so this is a very interesting phenomena. So at least for these situations you do have. So in effect, it actually says that, you know, mu P or mu dark O, they actually tell you, what exactly do they tell you in terms of the numerical semigroups? If I go back to the numerical semigroup situation, then you will soon see that this actually tells you that the ideal IS, according to the notation of Professor Herzog, this is basically your mu IS, and this mu dark AO is basically the cardinality of the Pseudorubinius. Okay, so this you will see why it is the Pseudorubinius very soon. Okay, and then the 1993 paper of Patil, where he actually gave an explicit calculation of this mu P for under the assumption that M0 to ME minus 1 form an almost arithmetic sequence. Now here is, I am kind of deliberately, I have mentioned it here. Now this happens to be the first Betti number of O, because see, there is also the very natural question which obviously comes, that what can you say about the free resolutions, about the Betti numbers? Is it possible to compute them? Is it possible to give a bound? Because these bounds on mu P and bounds on mu dark AO essentially happens to be, in this case, the bounds on the minimal number of bounds on the first Betti number, and mu dark AO actually gives you the bound on the last Betti number. So this is the interesting thing, that there is some you can say that there are some homological things also associated, but always the proofs, at least as far as I know, always the proofs are like a very detailed investigation of the numerical semigroups. And if I may say so, it is in fact the Apiri set which tells you, which gives you the maximum amount of information. Okay. And then this was my work with him, where we could calculate the number very, very explicitly. And for the monomial curve O defined by the almost arithmetic sequence, that means when the numerical semigroup is generated by an almost arithmetic sequence. So, and then eventually this also gives you that by type, I mean the Cohen-Macaulay type, because you will see soon that why am I saying that it is the Cohen-Macaulay type? Why am I saying that it's the last Betti number? That is because of, maybe I'll take you to that theorem first. Yeah. So it is this result of Jürgen Traft, where it was probably, yeah, so it is after his thesis perhaps. So this is the paper where he actually shows that the dir KO, the derivation module, the K derivations is actually minimally generated by this set. And this is your delta dash, if you remember, this is your Pseudorubinius according to that notation of ours, right? So this is the Pseudorubinius. So therefore you can understand that now the Pseudorubinius you have just now heard in Professor Herzog's lecture is the Cohen-Macaulay type. And it is also true that for this kind of one-dimensional situations, you have the last Betti number giving you the Cohen-Macaulay type. So therefore, the mu of dir KO, if you subtract 1, that is the one coming from here, then you are actually getting the last Betti number of the Cohen-Macaulay type, right? So this is the theorem which kind of has a lot of impact, and that is what has been used. And detailed counting gives you exactly what the Betti numbers are, the last Betti numbers are, or which is of course coming from this result. Okay. And by the way, maybe since I am saying Kraft's observations, I should say this also, that actually here you do have this result, which is a very interesting result, that if you have a symmetric semigroup, then you have this very nice upper bound on the mu dir KO, but then boundedness of mu p is still an open question for arbitrary E for a symmetric numerical semigroup anyway. Okay. Okay. So, and then eventually, I started looking at the homological aspects, or the syzygetic aspects, and this was the result proved with Philip Gimenez and Hema Srinivasan, that we could explicitly compute a minimal free resolution for the arithmetic sequence and in arbitrary dimension. I mean the m0 to me minus 1 when they form an arithmetic sequence. And the main work there was to show that it can be, this ideal can be written as a sum of two determinantal ideals, and then we could use the Egon-Northcott and the iterated mapping cone and some minimizing techniques. And then for the almost arithmetic, well, this is the only success story that I know, that we could prove this with students of mine, that for E equal to 4, we do have an explicit resolution. But unfortunately, I do not have any spatial structure for in general. Okay. So now I would like to say something slightly different. So the question is, these are the remarks that counting the Pseudorubinius gives the type and the last Betti number of O as well. And knowledge of Apiri set is important. Now, what I would like to say, that what is a current ongoing thought is, sorry, this is, yeah, sorry, I think this slide is repeated. Yeah, okay. So let us use this letter M for the multiplicity, that is the smallest non-zero element, or the smallest generator, minimal generating set you may take. Okay, and then clearly your Apiri set with respect to M is going to look like this, because these are the elements congruent to I modulo M, and I is running from all the way from 0 to M minus 1. There are exactly M of them. So you can write them like this, where K1, K2, Km minus 1 are natural numbers, right? And now this, you have already heard this, that these KIs, these are exactly the gaps. So if you count them down, the total number, that is what is called the genus. So basically, you know, in a numerical semigroup, from the Frobenius onwards, the conductor onwards, everything is there. Before the conductor, that means from 0 up to Frobenius, there are elements which are there, which are elements which are not there, that not there elements, they create the gap. And when these two numbers match, it is symmetric. Now the question is, like, how you, of course, there are many results regarding gaps and non-gaps, and you have already heard a conjecture from Professor Herzog's talk. Okay, so there are many things, but now what I'm going to say is the following. So for the calculation of the Apéry set, for the computation of the Apéry set, can we use this gap in a more effective way? So I would say an ongoing thoughts rather than ongoing work. So something that we are thinking with my students. So this is an interesting, so I would like to say it's an integer programming approach. That this is a nice observation by Rosales, which has been used in some other work also, that you can actually use these inequalities. And so this is basically the summation xi equal to g is also a constraint. And you are now look at the last two lines, that last four lines rather, there is a 1-1 correspondence between the semigroups with multiplicity m and genus g, and solutions to the above inequalities where we identify the solutions k1 to km minus 1. Remember, this k1 to km minus 1 are the gaps, and then their sum is the genus with the semigroup that has Apéry set. So if you know k1 to km minus 1, then you know the Apéry set clearly. There is no doubt about that. So these k1 to km minus 1, I want to see them as a integral solution, rather, I mean, non-negative integral solutions of these, if I may call it, a linear programming problem. But what you don't see is what is the objective function here, right? So this is exactly what is the challenge, and this is exactly what the thoughts that are going on, some experimentations are going on. So this is the function that we would like to optimize. And now in optimizing which sense? That's the whole idea. Okay, or rather you may take that if I know the m and the g, then this is summation xi equal to 1 to m minus 1, where m is the multiplicity, minus g equal to 0. So I want to minimize certain objective functions subject to these constraints. Okay. Now, of course, I can convert it into an integer programming problem. I can throw in some surplus variables, the standard techniques. And you know that there is a Grosvenor basis technique for handling integer programming problems, and that is pretty good. So if I may write it in the standard form, if this is my objective function, a1, a2, an are being treated as variables, and suppose I have thrown in lots of slack variables, and these are the constraints equations, and I am looking for non-negative solutions, okay? And then this n is the total number of variables, including the slack variables, and the set of all n real tuples, those we satisfying the constraints, is what we call the feasible region. But I am interested in the integer tuples, right? But well, this is the technique which people usually use, that you actually introduce a variable zi, and then you kind of write it like this. So zi, so which are how many zi's? M of them. Which m? So these m. There are exactly m many such equations, and throw in a zi for each one of them. So z1 here, z2 here, and then raise it to the power, okay? And then what you get is something like this, and take their product, okay? Now, why you are doing this is because this basically amounts to this kind of a situation, that if you have phi from here to here, and if this is your function, if this is the K-algebra homomorphism that you define on the variables, then this is an integer point in the feasible region if and only if phi maps to maps a monomial this to this. So you see, this now becomes a kind of a sub-algebra membership problem, if I say it in the language of computational commutative algebra. And then let me just show you that what we can do is that basically what we are trying to do is, if I may call these as fj's. So which are these fj's? These are these fj's. These are the fj's. Then basically what we are saying is that this subalgebra of which is a subring, question is, this is definitely the image. Now you have some monomial over here, you want to know whether it belongs to the image or not. Well, this is also pretty much effective. There are effective ways to deal with this, okay? So what would be the effective way? Well, we can give this kind of a Grosvenor basis technique, that what you do is you take just like the elimination technique basically. So you take the big polynomial ring, and then you take this ideal, and then you choose your monomial order, in fact, an elimination order, because what you want is that Zi should be greater than any monomial containing only Wj's, because you want to basically, you know how elimination order works. Whatever you want to eliminate, you kind of prioritize them. And then, well, these observations, these results, these are very standard results. For example, Cox Little Loschier's second book using algebraic geometry gives you a very good detailing about such things. Then you can actually show that this is your, this belongs to the image, because that is what you want by the previous observation. Okay. Now, this is basically some thoughts that is going on, because what I feel is that this is certainly not the most efficient technique as far as computing is concerned. Well, in fact, I was discussing with some computer scientists, and they really showed, suppose you take a typical Diophantine equation approach, for example, what is implemented in computer algebra software like GAP, definitely that much faster, at least for some small examples. Okay, but that's not the point. Point is, otherwise, if I'm trying to understand the Aperi set well, this could probably give a more clearer view that what kind of points in the, you know, I mean, it's kind of a better description, possibly. I can't claim it yet. There's possibly a better description of the Aperi set in terms of these integer points in the feasible region. Okay, and now my time is almost up. I'll just finish quickly. So this is another couple of things that, if nothing to worry if your constraints have negative integer coefficients, because all you have to go that you have an analogous theorem for the Laura polynomial rings, and therefore you can have a similar kind of result. So that's not a problem to deal with. Okay, so now this is a couple of questions that can one have analogous formations for the Aperi set with respect to any non-zero element of gamma. See here, we are dealing with only the multiplicity. Here the Aperi set is with respect to M, but well, Aperi set with respect to other non-zero elements, especially the, especially when, if you are, for example, if you are studying projective closures, Cohen-Macaulay-Ness, it does matter, right? So these are the things. And also for the Aperi table, which gives you the good information about tangent cones. And this is the last thing I will say, that this is a theorem in Patil's thesis where he actually gave a generating set for the defining ideal in general. That means without any assumption on the MIs. And well, it definitely is technical. There's some technicalities. And this is what it has been extended to. So this, in fact, from that result, Patil could come up to a minimal generating set and things like that. And back in 2003, I could show that it is in fact a Grobner basis. And this is what a result by Brzezinski, Curtin, and Stuckrad, they call it a Patil basis. And in fact, they have a more generalized notion in terms of the row degree. And they in fact show that even that is a reduced and normalized Grobner basis with respect to a suitable term order. Okay, so I think I'll stop here and wish Professor Patil a very happy and successful life ahead. And thank you for your attention.
So thank you very much for your talk. Are there any questions or remarks? Nobody? Okay, so I thank you very much again.
Thank you.
And we have a break now, I think, for 15 minutes.